Okay, so now we're going to learn about some of the cache systems, the cache models, which are in gem5. Marjan's going to be talking about this. And then we're running a bit behind, so I think we'll probably just do lunch after this session, which will be 45 minutes or so. So a bit early for lunch. And then we'll pick up on CPUs after lunch. All right, here you go, Marjan.
So hello everyone, my name is Marjan. I'm a fourth year PhD student here at UC Davis. I'm also a very fast talker, so any point of this talk, if you have any questions or you just want me to repeat myself, please go ahead and ask. I would love to do that. So like Jason mentioned, oh, okay. I'm going to talk about different models of cache in Gem5 and how we can use them in our simulations. So just before we start, to save some time, I want you to build Gem5 with the Ruby. So all I want you to do is that to go to Gem5 directory and just run this command line, which is scans build, which you have done multiple times, I believe, so far. Build, and you want to run it with null ISA, which is because we want to run traffic generators, messy to level, which is our coherency protocol, /gem5.opt, default, basically your ISA, your protocol, and you can just skip the slick HTML if you want to, but if you can just copy that, you can also do that. And just run it with 17 cores here to make things faster. So I'm going to take a minute so you all can run this. If you have any questions about this or if you get compilation error, just let us know. I hope you all are able to do this. All right. I'll give you a few more minutes. Alrighty, let's start then. So we have two different cache models in Gem5. One is classic cache, which is more simplified, it's easier to use, it's faster to simulate with. And the other one, which is more in detail, which is Ruby, that comes from the Gem simulator. And it's more in detail, and it has a very detailed coherency protocol and an interconnect model. So when I talk about caches, it's not just about the storage, like the cache, actual cache. It also incorporates the coherency protocol and how everything in our cache hierarchy are connected to each other. So just to give you an outline of this talk, I'm just going to talk about the coherency a little bit. I'm sure you all know this better than I do. And then just jump into the simple cache and then Ruby. So why do we need coherency protocols? Is because we might have multiple number of cores, and these cores have their own, they want looking for a cache line, or they might share a cache line. So once a core has written something in its own private cache line, it has to let other people know that its value has been changed. Otherwise, the correctness will be jeopardized. That's why we do need coherency protocols. So there are typically two coherency protocols. One is Snooping, the other one is directory. I can say from now that the classic cache uses Snooping, and Ruby uses directory-based cache coherency protocols. So a Snoop protocol is basically when you have a shared medium, which is here is our shared bus. That's basically whenever you're looking for a cache line or you're updating a cache line, you send each core send a request to this shared bus, and at the point of and it's basically the point of arbitration, and it starts basically looking for that cache line and broadcast that request to other cores so that you can find that or change that or something. And so obviously this is not very scalable, and it also has a lot of traffic that needs to be communicated through that bus. That's why there is also a directory-based coherency protocol, where you basically have a number of directories that keep track of certain values or certain cache lines. And when you're looking for that, you basically ask that directory. If you're updating that, you let that directory know so that it can invalidate those cache lines in other private caches or something. So far, any questions or anything? All right. So simple cache, like I mentioned, uses a snooping protocol. It's not something is in detail. If you want to change something in your coherency protocol, or if your caches have a first order effect in the results that you want to see, then it's highly recommended to not use simple classic cache and use Ruby. So, but if you want to just basically have like a cache hierarchy there, then it's better to just use simple caches. So there are three types of basically sort of interconnect or crossbars that are created for simple cache. It's a non-coherent crossbar. The name suggests what it does. It doesn't. So it's not for maintaining coherency. We have a coherent crossbar. We also have two specialized versions of this coherence crossbar, which is L2 crossbar and system crossbar. I'll talk about this a bit. And we have a Snoop filter. Again, I'll talk about the Snoop filter in the next few slides as well. So the coherent crossbar is a simple snooping protocol. You basically have a cache. It's the same basically algorithm and everything else. As I mentioned, we have L2 crossbar and system crossbar that are basically a specialized version of this coherent crossbar, right? So what is the difference between these two is that the only difference between them is that the width of these crossbars are different. The different pipelining latencies in these two are different, and so on. So you can also change that as you desire based on the architecture you want to design. The other one is a Snoop filter. So I look at a Snoop filter as something like between a snooping and a directory-based. It's near directory because it has a directory, but this directory is not for all the cache lines. It's for each of their cache controllers. So you still have the shared medium. You still have to broadcast your request, but instead of going to the cache, fetching that cache line, searching the tag, you just ask the directory whether or not that data exists in that cache or not. Any questions so far about the Snoop filter or the other one, coherent crossbar? All right. So this is just like a little bit of like a high overview of what I mean by basically having a deeper cache hierarchy. You basically in this system have multiple cache through L2. Again, this can be even deeper. It's not like basically limited to this two-level hierarchy. It can go even deeper than that. So you basically, that's a very good question. So you basically ask, your private caches ask the LLCs, and these LLCs ask those memory control. The L2 crossbar asks the LLCs whether or not that cache line exists in that particular LLC. What is the status of that? If its value has invalidated, through that L2 crossbar, will basically that invalid will communicate to the different cores. So that also is something that you can specify when you're instantiating that cache, yes. So I believe you did an example of a simple cache, like a classic cache yesterday. So there are multiple options there that you can, based on your design, you can change. It pretty much has all of the options that you need to change. So again, I believe yesterday you have done this, but just like a reminder, So when you build your system, there is a cache, basically a source code for a cache and non-coherent cache that's being created. You can look at all of their parameters in the cache.py, and you can just basically instantiate your L1 cache, L1 instruction cache, data cache, and L2 cache, and you can change, like you mentioned, all of the parameters that you want to change. For instance, the size, the associativity, the MSHR entries, and all of those things that you want to basically change, you can change here as something that you want to basically use this cache for. All right. Any questions? Okay. So let's jump into Ruby. So Ruby is much more complicated than classic cache in a way that it basically defines the cache coherency protocols much more in detail. It also uses directory-based cache coherency protocol. And it also has a very sort of extensive implementation of the network on chip that we'll talk about in the next few on Thursday. And yeah. So if we want to look at Ruby, what is Ruby? It's basically is a structure between your CPUs and memory. It describes connect and it describes your coherency protocols. And it can be connected to your CPUs and memories through classic ports like request response ports. What Ruby does more in detail is that it creates this different controllers for your components in your cache hierarchy. For instance, it creates a controller for your L1 cache, L2 cache directory, DMA, all those sorts of things. And it has a network on chip that way that you want to test this. Change something on your network on chip, you can basically change this network on chip here. Or you want to add more coherency, then you have to change the L1 cache, L2 cache, or direct. So I can characterize Ruby for you in 4 ways. So it has a definition for your controller models on your coherency protocols. It has a topology, basically, like I mentioned, how these controllers are connected together. It has a network model, which network model basically specifies what kind of network technology you're using, what kind of switches or links or link latencies, those sort of things you're using. And then interface, basically how this Ruby is connected to all the peripherals, all the CPUs and memories and so on. So today, I'm going to talk about the controller models and the interface. The other two, we're going to leave that on Thursday to see how is that implemented in Gem5. So in terms of controllers, so the way these controllers are described is through a SLIC. A SLIC is basically a domain-specific sort of language that creates the like a state machine for each of these controllers. And once you compile this SLIC will be basically, this SLIC code, a state machine code will be compiled into a sort of like a C++ code and Python code that you can basically read and instantiate in different ways or give different values to or connect them to different things. So the other thing about this is that the way communicating with this state machine are through output message buffers. That again, these are your specific to your coherence. We'll see how we can basically connect these sort of message buffers. And for different components in your system, DMA, everything else, you have a specific state machine that you need to, if you want to change your coherency, you need to describe. So the way we compile this is that we use the same sort of command line that you use at the beginning of this session, where you specify your ISA. Is it x86? Is it ARM? Is it whatever? And then you specify the cache coherency protocol that you want to use. For instance, the way you did it, you used MESI 2-level protocol, and you just basically pass it to this. And a SLIC HTML, what it does is that it creates an HTML file at the end for you that basically tells you how the states and everything else are connected to each other. Good if you want to change something in your coherency protocol, just goes at the end when you compile it, that matches your expectations. And once you compile this, there is this file created in your build directory basically has the code for your L1 cache, L2 cache, DMA directory, for controller, so you know exactly how to instantiate that in your config file to be able to use this. So I know I gave a lot of information right now. So is there any question or is there a confusion now? So we'll see a little bit of example about this in a few next few slides. Hopefully, if there is any confusion, it can be solved there. Yes.
Command line arguments like protocol, slippage, can those be written in the build-ops?
So these are parameters that you give to a sconce to be able to create this sort of binary for you. So what it has is you have to specify. So the way you run it right now, your BTS sconce, is that it only uses a classic cache. So if you want to specifically tell your sort of to build your binary with a specific coherency protocol, you have to specify that coherency protocol. For instance, at the beginning, we built this using Messi 2 level. If you want to change your coherency protocol to something else, like Moesty Hammer or something else, you have to specify that in that protocol over there. Did that answer your question?
Why the command line and not within the build-ops?
So you can also add that in your build-ups as well. So that you can do that as well. But this is more like sort of systematic way of doing this. So you can basically just say null here, like x86 here, run it with different protocol, but the way it's created is not with simple cache, it's with, for instance, Messi 2 level. Yeah. Yeah, it's totally fine to basically just skip the rest and just do null Messi 2 level here, for instance. Any other questions? All right. Okay, so let's see how, when we compile this, how it's going to look like in your build directory. So for instance, for L1 cache, like I mentioned, we have a slick state machine, which is connected to a bunch of message ports, right? So we have so now we sort of replace this slick state machine with the L1 controller. So some of the things that you will see in your Python code, some of the things that you need to specify to be able to connect this to other components in your cache hierarchy are, like we talk about sequencer and all those things, but more specifically, the last 5 lines in the bottom, which are the message buffers that are created. So we'll see in the next few slides how we're going to use that. This is how we're going to use this. So this is just a very, very, very small sort of piece of code to basically describe L1 cache in your any config file you want to write. You inherit from that L1 cache underscore controller, and you specify like basically your cache memory system. Oh, so you have to you have to ask for 2 questions here. First here. How are you going to connect this to other components in your system? So how are you going to basically define your cache is through, there's a mouse here, okay. This self.cache memory, which basically you describe a Ruby cache, you give it a size, you give associativity, you specify what part of the address space it has to go read to be able to address this cache. And then to be able to connect this, you can create a connect queue sort of function here. And we'll see in the next slide exactly what that connect queue does. So just forget about the queue. What you do is that you create connect this message buffer to your Ruby system. Basically connecting your configuration files to this port of this L1 cache controller. Any questions? Yes.
What comes to the buffers? Like, why store buffers?
So these buffers, what they store is the Ruby requests that we'll see in the next slide. What's going to, like in the next few slides, how it's going to be. So it's basically you have a state machine. So for instance, in the cache coherency protocol, you have to send sort of like messages or requests to each other, right? So this message buffer is storing those sort of information, if I'm not wrong. I'm not mistaken.
I'll expand on that a little bit.
Okay.
So in the
So to be able to just use Ruby, like the current existing coherence protocols that we have currently with Gen5, all you have to do is to basically connect these message buffers to the right ports. Okay. So we have a Ruby system. We define different controllers inside of that Ruby. We connect the ports together somehow. And now, how can we connect this Ruby to like your CPUs or your memory controller and so on? So it's a bit different than classic cache when you want to connect that to a CPU, because right now your Ruby system takes Ruby requests and not like classic sort of request that your CPU sends. So what we do here is that we use a sequencer here. And the sequencer, what it does is ultimately just return what's there, converts Gen5 packets into Ruby packets and send them to Ruby. And that mandatory queue that you've seen here is basically be able to store those, basically receive those requests from that sequencer. Any question? So this is how we are interfacing our CPU with the Ruby. On the other side, when we want to connect something to a memory controller, we connect them through the classic ports, the classic request and response ports that we have right now. This is like a small, like a high-level figure of how things are connected. So for instance, you have multiple CPUs. You connect these CPUs to your L1 cache through a sequencer. You have some sort of network that we'll see on Thursday. And this network connects your basically controllers, like L1 cache, for instance, here with directory. And these directories are connected to the memory controller through request and response port. Yes?
Do you know how much overhead the sequencer adds?
Excuse me?
Do you know how much overhead the sequencer adds? Is it a lot or?
So I believe that's part of the things that makes Ruby a bit more slower than the classic cache, if I'm not wrong, in addition to the whole state machines that we're adding. Yeah. So it has to do conversion, right? So it's not as easy as classic cache, where you just like read that. Okay. So again, just like an example of how if you want to create sort of like a one-level cache, how do we do this? So first of all, you are creating your L1 cache and directory controller, and your directory, controller, and basically the number of your L1 cache, because they're a private number of CPUs. You, for instance, have one directory here. You create a controller based on those L1 cache and directory controller. You use a sequence, you basically instantiate a sequencer. So the number of sequences are the number of CPUs, which are again the number of L1 caches because they are private. And you connect the CPU at this point to CPU and the other point to your L1 cache. At the end, you are connecting your directory controller to your memory controller. So you might ask, okay, how are we connecting L1 cache to this directory? And again, we'll talk about it on Thursday. So now we talked about this. Let's look at a bit more like a complex example. So here we have, we want to run like a simple configuration file with Messi2 level. So Messi2 level has a private L1 cache and a shared L2 cache. In this case, we have 4 CPUs, 4 L1 caches, 1 L2 caches, 1 directory, because we only have 1 memory channel here. And OK, so I believe you built this. Hopefully, it's finished so far by now. So all I want you to do is that go back to your bootcamp directory and just run this code. So what this code does is basically you're calling your binary. You are calling this simple cache Ruby, which we'll see in a minute. Oh, it has 2. You can't just do it with 2 caches. So 2 CPUs. So it's number of the CPUs. Let's just do 2 CPUs, Messi2 level, which is the coherency protocol you want to use. And 512 megabytes is basically the size of the cache and the size of the memory channel that you're using right now. And you can just run it and see that it will run. And then we can look at the code and just go one by one to see how it looks like. Where is the? Oh, here's. Oh, OK. Yes, I'm sorry. So if we take a look at this config file, it's actually pretty easy. So it has, as you can see, it has a couple of arguments. So one of them is number of cores that you want to have. The other one is a type of cache system that you want to use. Here we only have two options, classic and message level. Yes, and we also have the number of the size of the memory that the system is connected to. So let's just skip the classic part and take a look at the message level. So there is this. So in your standard library, in your components, in your source, you can basically instantiate this message level, and you can give different values to this. For instance, here you can specify the size of your caches and associativity and so on. So you instantiate this, and inside of this message level, which we'll look at in a few minutes, you can see that you have a class for L1 cache, a class for L2 cache. You also have an interconnect that connects everything together, which is right now just a simple all-to-all interconnect. And yeah, I think that's so far. Let's take a look at this message level cache hierarchy, which if we're looking at, we go to gem5 source, Python, gem5 components, and if you go to cache hierarchies, Ruby, message level, you can take a look at it. So we basically what we have, go back. Yes. So you have basically, you're specifying the number of L1 controllers here on the specific sort of components you can give to it. You also have a connected components, I believe here, for this, if I'm not wrong. Yes, I think if you go to L1 cache, you can actually take a look at that and see this. If you go, I think, caches, message level, you have basically here an L1 cache, which basically you can give different values to. It also has a connected components here, connect queues here, which is exactly those sort of queues that are coherence-specific message buffers you can specify here. You have one mandatory queue that will be connected to your sequencer, ultimately will be connected to your sequencer, and you have a bunch of these sort of message buffers that are connected to your Ruby system. So again, if we go back, so the way we just do this is that these are already created. So you have a class for L1 cache and a class for L2 cache. All you have to do is just call them, give them specific values, and just say how many number of these caches you want, and then connect everything together. And it's like at one side connect them to a sequencer, and the other side connect them to your memory system. Go back here. Okay. Yes, here we are. And that's exactly what's done here. Yes, and you can see here this basically how your cores are connected to your sequencer. And the other thing I forgot to mention, we run this with traffic generators that was discussed before, and that's why we're using a null as sort of our ISA here, because you just basically just a traffic generator with load and store requests. All right, any questions about how to use classic cache and Ruby in gem5? All right, I guess I'm done sooner than I expected. Yeah. Yeah, I can run it. Oh. Okay. Oh, no. Oh, okay.
It's already in thing, so gem5, type in gem5 dash yes.
Okay. Um, what else? Five. Ah. What did I do that? Okay. Oh, of course. Oh, what the heck? What? Oh. Oh, yeah. Let me find it. No, don't have that. What? Isn't it inside of the caches? I think it's inside of the cache components. Okay. Uh, All right. I unfortunately didn't build this when I told you to build this. Oops. So, do you guys have any questions about, or were you able to run this successfully? Yeah? Okay. Any questions about this? Yes, please. Slide 26 and 7. Let me, which is 26. Oh, okay. So this is just basically saying that at one side, it's connected to a sequencer to the CPU, and the other side, through classic ports to the memory system. Yeah. So it's basically you create this cache system. You know exactly how to create. Like basically, Ruby takes care of creating these controllers, use different network on chip models to connect everything together. But okay, now you have this Ruby system. How do you connect it to the CPU? How to get the traffic, like store the traffic in the memory, and so on. So you do that through, so basically interfacing this Ruby to other part of the system. So again, we're using sequencer to be able to connect this to the CPUs, to our cores at one point, because there needs to be some sort of sort of conversion between the requests that we're getting from the CPU and the requests that we want to create, want to store, or we want to pass through our controllers. And the other side, since the directory already creates sort of like a request to the memories, so we can basically just connect everything together through a simple ports, which is a simple request response port that you have you have been using so far in different shape or forms. Yes. Slide 24. Yes. Let me just make this bigger. I believe, at least in Snooping, I know that it needs to be ordered, so I guess here it has to be ordered as well. I think maybe there is another thing is that it might be something that's coherency dependent, or for different coherency protocol, you might be able to change this to, you might not to have unordered. Based on your coherency protocol might have basically jeopardize the correctness of what you're running. Yes.
This might be basic in our architecture question, but can you say more about the directory-based cache coherency protocol? It's like the other one.
Oh, Snooping? Okay. So in a Snooping, you have this like a shared bus. So whenever you want to, you're writing something in your cache, or you're looking for a cache line, you basically use this CPU. Use this bus as a point of your arbitration. You send a request in a queue, and that's basically at each time, each of these Snooping requests will be reside on this bus. And this is basically a point of sort of consistency between all of your your controllers. So they see all of these requests all in order. So whenever, okay, I have this cache line in my, for instance, last level cache, oh, I have this cache line, so I just basically send that back to that. In directory, so you really having a bus is required to be able to maintain coherency in Snooping protocol. I mean, come on.
You can do Snooping without us.
Okay. You can have the Snooping, okay. But in directory-based coherency protocol, you have basically this sort of like a directories, which are just like a bookkeeping sort of modules that tells you, okay, this request or this cache line exists in some controller somewhere, or if it needs to be invalidated, it also let other people that have the copy of that know that it needs to be invalidated. So yeah, so this is so it's not something that's communicated between all of your controllers. It's something that's communicated to your directory controller, and your directory controller can let other people know basically what to do. So yeah, so in a directory-based coherency controller, you can have different topologies. Like you can have sort of like a hyper mesh or something else, and still you have your consistency is maintained.
So there's like no valid bits and stuff like when you're using a directory.
Mm-hmm.
Like it's just like all the validity is kept up in the directory.
Yeah.
And like okay.
That's exactly it. So basically, I mean, I look at it as like a bootkeeping.
So you put your local view of it. So like you know that you have this cache line and it's in shared state or it's in modified state. And the directory also knows that you have the cache line in whatever state it's in. And then if you need to do anything with that cache line, you have to communicate with the directory, which will coordinate with all your caches.
Yes. I don't listen. I can't. Oh, so it did multiple, basically, message buffers, right? I think message buffers, right? So why do we have like a response from cache? That's the thing. Sequencer? Okay. The next one? Okay. I have.
Why do you have two memory controllers instead of one memory?
Oh, you can have as many memory controllers as you want. Oh, so this is not like a sort of shared thing. So you can have different memory controllers and connect these memory controllers to your Ruby through different response, or to your directory more specifically through dedicated response and request sort of ports. Can I come closer? okay. So the thing is, every request that you get, it's either reading or writing something, right? And it has like a specific address. So this address basically goes to a particular memory controller that's in charge of that memory channel that has that address. So it doesn't really, it basically has a certain destination or certain memory controller it needs to target. Okay. Any other?
Any other questions?
Yes. Slide 15? Okay, yeah.
What does the options writeback gain mean? Does it mean that if we have writeback and we set 30 minutes of the cache life necessary, then all the option means?
What does write back clean?
Oh, what is write back what?
Write back clean. What does write back clean?
Oh, okay, okay. So it's basically write back clean is sort of like, so it's like a eviction. So it's basically some of the ISA they require whenever you want to write back something, even if the cache, you want to evict something, even if that cache line is clean, you have to write it back. Other ISAs, it's not particularly the case. So if this cache line is clean, you don't need to write it back. So for them, this sort of, what is it? I forgot the name. Evict clean is going to be false.
So it's particularly useful if you have an exclusive hierarchy. So if you want your L1 to be exclusive with your L2, then your L1 needs to do write back cleans to insert it into the L2. So this is a little bit, this is basically the